So good evening. Hello, everyone. My name is Tobias. I'm here to talk about how I fell in love with Zephyr, a system architect's tale. That's typically what I do in my day job. I'm a system software architect, mostly for medical devices. I've been doing this for the last 15 years. And I've seen a lot of things happening during embedded device development. And the one lesson I really learned early on is that to be successful with embedded systems design is that you really need to think about systems engineering explicitly. And that's what I want to bring to you. And what I learned is such a nice fit with Zephyr. We started all of this a long time before actually Zephyr appeared in 2016, but we've been following a friend of mine and myself, Stefan, who is not with us tonight, so apologize for that. But we've been following Zephyr ever since its initial release, and we really, propose using Zephyr for all of our embedded system designs from now on for firmware, just because the fidelity and the maturity of the tools and the abstractions that Zephyr offers, and that's what I want to show you. It's a bit of a nerdy talk. I gave that talk in Prague last year. This is the shortened version, so if I'm running too fast, there is a YouTube video where I think it's a bit slower because I was allowed 40 minutes rather than 20. And it is still technical because it was on the advanced track, but I did ask Susan and she said, no, come. So I do apologize if some of the stuff might be a bit too technical. Don't be afraid, come to me in the break. Ask me any question you like if some of the stuff won't make sense immediately to you. So Stefan is also, just a few words on him, a senior software engineer. His background is Linux, so he's been doing Linux development, kernel development for 20 years now, so he's a bit older than me. And we together founded a GitHub organization called TX Systems. There's a third guy missing here because TIAG actually means three as a company, but our third guy is more into embedded Rust, and he would love to also be on a meetup once Rust has landed on Zephyr proper, but so far it's just the two of us. If I were to describe myself with one hashtag, it would be FOSS for medical, because that's the two passions I have, free and open source software and the medical device space, and I try to bring these two domains together as much as I can. That's what drives me. And what I want to talk about today with you, or what I want to share with you today, is how I typically approach embedded systems development and in particular medical devices. And as I said initially, I'm typically starting or joining projects as a system architect. And then my job really is to and that is a very schematic view, just to understand where the problems are, to elicitate on the requirements with the user needs. That might be biologists, typically in my case, because I did a lot of diagnostics devices, particularly through the COVID pandemic, as you can imagine. And a couple of the examples I'm going to show later, they all came kind of from that area. And then the first thing I typically start to create is a system model, an explicit system architecture. You might have heard of something like SysML. Version 1, version 2 is just about to be released. There are some expensive tools that you need to use for that, but it is a queryable model, and then this model needs to be translated down into what I now call the MCAT model. That's typically what the mechanical engineers are doing. There are ECAD models. We already saw one from David on a PCBA, a printed circuit board assembly. And obviously, we have software models, UML diagrams, and the actual firmware. And it's really these interfaces that are hard. This is really where most of the embedded systems projects lose time, where the friction kicks in, where misunderstandings happen, where things are being misinterpreted and just things won't work. And that's where my focus is, to remove these frictions. And this is where Zephyr helps me so much. And that's what I want to go through with you in a bit more detail. This is a bit annoying. I hope it still works if I do it like so. To start with, I just want to give a really quick rundown, probably a lot less than 2 minutes, on Agile hardware. That's how we typically approach hardware development. I found a company in Berlin that we typically partner with who has helped us to develop this idea of agile hardware. And what we mean by that is we'd like to have similar iterations in hardware developments as we know them from software development, like a new board in 4 weeks or even in 2 weeks. And typically, electrical engineer would tell you that's not possible. We need to capture the requirements first, and we do a big board, and we put all of the board on it, and then it works the first time it comes from the factory. That's what I typically tell you. And nothing could be wrong, more wrong than that, because it never works the first time when it comes from the factory. Anyways, we tried to solve that puzzle, and that actually predates Zephyr. But as you will see shortly, it kind of made so nicely with the ideas that Zephyr brings eventually. And the idea was that when we started, we found that in electronics design, as you might know, there are actually 2 levels of models or 2 levels of designs that happen. There is the schematic capture. That's when we get the schematic. It's a PDF. It just you showed that as the first screenshot. And then there's what's called the design, the PCB, the printed circuit board, where you have copper traces and footprints, where the parts will land on the board and so forth. And from one schematic, and that was the key realization, actually you can derive multiple of these designs. You can make large, clumsy, big PCBs with lots of debug connectors, lots of LEDs for pretty much every signal that you want to have, or a connector for logical analyzers, all of that stuff. And then eventually, from the same schematic, you might also be able to derive what we then call the form factor PCB. So that's what actually goes into the product. And if you keep that freedom for long enough, you can actually very quickly iterate on separate modules. And for the purpose of this talk, I'm considering myself with 3 functional units. So that actually is at the system architectural level. That is the functional breakdown of what that system's supposed to do. I have 3 functions, or actually a 4th function, which is control. That is the microcontroller. And then I have 3 functions, heating, movement, and an analog front end, because I want to sense something. So that's what I call a development rig. And the idea is that these PCBAs can be developed and changed independent from one another. And eventually, we bring them together in one single schematic towards the very end. And the company I work with, as I said, they helped me building scripts to do that even automatically. So that's the idea of agile hardware in just a bit. And the main point is that the relevant interface between hardware and software, as far as we are concerned, is actually the schematic. It doesn't really matter. The software doesn't know what the PCB looks like it runs on. It is all about the schematic, which pin goes to which pin, what device is on which I2C bus. And in Zephyr, as you already have heard, the language by which that is being expressed is the Devicetree. And it is explicit and separate from source code. Typically in embedded development, if you've done something with FreeRTOS or any of the other systems, that is done by preprocessor defines in header files that you have to manually edit. Now, Zephyr under the hood actually also translates to preprocessor defines in headers, but you do not have to do that yourself. There is a machinery that does that in a much faster and a much more consistent way for you than what you would typically end up doing yourself. And that's what it looks like. So that's not talking nuts. That really happened. So that's what one of those rigs looked like. Actually, that was also an application processor. So for people who are in the field for a bit longer, that's a Beagle board. They were quite famous like 10 years ago. But what you see here is actually the core board where the microcontroller is, a shield board where we just had a lot of connectors going off. And then we had these functional units. You see the motors attached to one. And the same schematic, minus the Beagle board, admittedly, but all of that stuff eventually was collapsed down to this form factor board by the process. And it did run the same firmware, the binary, the same firmware. And that is a big one for me in medical, because I want to start the validation and verification process of my software as early as I can without having to do a lot of rework. And that's why I want to make sure that whatever did run on here, and I have already written tests for, and I've already validated the stuff, will eventually also run then on the form factor board, which might come a lot later. So how do we do that? For A quick, just to make the what's come a bit more explainable, I will now collapse the core and the shield as concepts into a single board, which I call the control board in the slides to come. And I will also collapse these independent modules just into a single board for the purpose of this talk, which I will call the peripherals. So in your head, imagine I have a rig, which comprises a control board with a microcontroller and a board with all the peripherals that I need, a stepper motor driver, an LF front end, and maybe a heating element, right? So at the system level, they're equivalent, but the right one actually is a lot simpler to set up if, for instance, in a science lab. That's where these things actually went to help biologists figure out a good COVID testing strategy. The first thing which I really was very much, which I really appreciated from Zephyr was that in the software architecture, we already see a nice, we're already able to decompose the system. That's not Devicetree yet, that's just Kconfig into several functions. And from my functional architecture, which I kind of draw here, I have services, an RTOS, there is a shell, there is some remote procedure call invocation for whatever purpose, and there is some service that like what also David was showing, that just retrieves sensory data and streams that out. We call that the data scope. And then I have functions, heater, motor, AFE, and they can just provide bindings into these services. So that's an open-close architecture for those of you who've seen that before. And Zephyr has all the things built in for you to realize that in a very clean and reproducible way. And how that goes, let me briefly show. That would be a source tree structure for one of the subsystems, let's say the heater. And then for each of the services that we found, we just have individual C code files so that eventually in the final product, when I might not need the shell, I just switch off the MQT, the heater shell.c compilation unit from the build, and it will be excluded from my product build. But during development, I can use the Zephyr shell. Probably all of you have seen, or most of you have seen the Zephyr shell. It is just such a handy tool that you just don't want to miss it during development. But in a final product, probably for security reasons, you really should reconsider whether you keep it in or not. And that's what the subsystem, maybe I'm a bit quicker now, that's what the CMake lists TXT look like. They can also, it's not only that the C code can respond to these Kconfig symbols, it's also the build system that can respond to these Kconfig symbols, so that you have like conditional compilation, which is also makes life a lot simpler. And there's even one more nicety. If you have like what we had, very many of these similar functions, you can also make very similar Kconfig symbols like subtrees in your Kconfig tree by using what's called Kconfig templates. That's an addition of Zephyr that is not upstream in the Linux kernel. Most of you will know that Kconfig actually comes from the Linux kernel, but this templating engine is actually something that is unique and was introduced with Zephyr. And we made use a lot of this. So we have that template, and it's been instantiated for each of those subsystems, giving me consistent, searchable, by regular expression, Kconfig symbols. So that's just something we are now doing and proposing and recommending for all the systems we're working with. Now coming to the Devicetree, if anyone would just show me how many more minutes I have. I think I'm at -6 now, so maybe if I'm approaching -15, give me a nudge. Devicetree, and that's really where we also learned a lot. So I'm going to show you now a couple of iterations that we went through, starting with the simplest and our very first one, and it's also a wrong one, as I would call it today. But nonetheless, it worked. And I just trying to explain to you what we improved from one step to the other and how that came about. So the first thing is, and that is actually what I had on this very first slide, I need this mapping between the hardware world and the software world. In hardware world, I have two boards. I have a control board, I have a peripherals board, and there is some cabling in between these boards. And at the device tree level, in the first instance, we just created a single device tree that we call Devicetree. So there is already some loss of information in that mapping. So I hope this is clear, but it works nonetheless. It was already mentioned, Zephyr comes with these 600 boards or whatever it is, but typically what you want to do in product development is you want to create your own device tree, your own hardware product abstraction. So under boards, you will create a Devicetree, and I have to apologize, but luckily it's just on main, it's not released yet. This is all pre-hardware model version 2. So whatever I'm showing is just the old, but there are not that many differences actually in the invocation. For what I'm talking through here, the differences are really small. One important thing that we learned, which will make your product a lot less fragile and more future-proof, is to use device tree symbols. And we saw that in on David's slides already, dt get node, dt spec get, to focus on aliases, Zephyr user, or dt chosen nodes, because that is where you do some mapping in the device tree. Do not go deep into the device tree to pick symbols up, because they are subject to change if you go from one board to the other. There is this system level mapping at these 3 nodes, and it depends on the context which of those nodes to use. Typically, we end up using a lot the aliases nodes and just do a mapping at this level. That's what it looks like. And again, I'm not going through the details. That's a typical excerpt from a device tree. And as I said, it depends. Here we were still using Zephyr user, not the aliases. But these are the symbols, the labels, which are being used or picked up by the subsystem, by the code. Right? This is where the binding happens between the software world and the hardware world. So as long as I provide a different hardware that still has semantically equivalent definitions for these symbols, my code will compile without any change. I do not need to touch the C files again, and that was our premise. We do not want to touch a C file again if we change the hardware, because it's separate reasons to change. Code changes for function, and the hardware, the device tree changes for hardware changes, obviously. The problem was, as you can see, that we have a direct coupling between our peripherals, this is a stepper motor driver, our peripherals, and elements of the core board. So the timers 8 is from the STM32 that we were using, so we are making a tight link between details of the core board and details of the peripheral board. So we are lacking in abstraction, basically. That's what I'm saying here. And the problem came into being when reality knocked at our door for the very first time, because the scientists were doing the first tests, and they found that actually the motor stepper driver that was doing some pumping wasn't strong enough. So we had to do a respin of the motor board. Like in our language, we had to do a respin of the peripherals board. But the core board didn't change. But we only had Devicetree, so it didn't really work out. We only had the device tree for Devicetree, and we wanted to support both rigs. That is another anti-pattern in embedded development. Fast forward, you can only, the moment the electronics engineers drops the next version of the board, the firmware is changed so that it will never ever run again on the previous version of the hardware. You should avoid that. The previous hardware is still good for a lot of stuff to test, and it's still good for comparisons. So make sure that you keep your software running and compiling and building for your already and previously built hardware models and hardware boards. So, but yeah, we had two peripheral board revisions, but only one core. So what to do? That's the question. And the answer is, as usual in software or in information technologies, you solve the problem by introducing an abstraction, right? That's what you do. and that's what we did. We actually resolved this DevRig into what it really was, and the concepts in Zephyr are board and shields. I guess most of you have heard about shields already. They are like overlays. They add additional things to your board, and the typical invocation is -b control. This is the board name, and then more stuff to come, dash dash, and then a CMake variable that's called shields, and then you provide one or more shields that will be added to your Devicetree compilation. Actually, I just wanted to do something which I didn't do in Prague. There is recently merged a PR 72720, which introduces a new, and I really liked that, a new variable --shield on the west build command, which gets you rid of these lengthy -d shield variables, but that's upstream. And the way it works is, these are shields now. Peripherals is a shield. You have version control. You can have version 1, version 2, and they will then pick up by the cbuild mechanism the overlays belonging to the right control board. So I can now say, and that is the important one, not doing the details too much, I have a control board, and I want to use peripheral version 1 or peripheral version 2, and it both will compile and both will build. So I have resolved the abstraction problem that way. Looking at this, you see that the actual overlay is empty because we haven't done a lot yet. It is all forwarded to the control overlay. So this peripheral shield would only work with this core board. The details are captured in board-specific overlays to a shield, which is an overlay. So it's a bit of indirection, but that's what Zephyr allows you to do, and we found that quite useful for the reasons I mentioned. And you see here that on the version 2, there were more channels available on the analog front, and as I said, there was another stepper motor driver being used as well. But that wasn't the end of the story. We then later had to build 200 of these additional rigs because they really want to do batch processing by life science. They really have to do lots and lots and lots of testing. The problem was, it was Corona, and pretty much every supply chain just had broken down. So we just couldn't get the parts anymore. We couldn't build our boards anymore. We couldn't buy the STM32F7 chips, but what we could do, and what we eventually ended up doing, is we still could buy Nucleo F767 boards. So there was another board, another core board of sorts, the Nucleo board, that we could purchase, but our peripheral wouldn't talk to it, right? So how do we make these things fit? So how can we model rigs with Nucleo rather than core boards? And again, something that Zephyr provides us with is we can introduce yet another abstraction. To this point, the peripheral was explicitly bound to the control or to the core board. We now made the interface explicit by introducing a new symbol, which we call the connector. And again, this is also something that upstream has been done with the Arduino connector, just to introduce something that the peripherals can depend on, right? So you know from architecture, software architecture, that you should not depend on details, you should depend on abstractions. And that's exactly the realization of that principle in hardware world. So a lot of stuff carries through. I'm a bit quicker, Susan. Just give me. And this is how it looks. There are so-called, and this is, as I said, this is a bit of a nerdy theme, but come to me and I'll try to do my best to explain what a nexus connector is. So basically, it's a mapping from one Devicetree structure to another, just to show you what's possible with that technology without going into the details. And then I have a mapping in my control board that the I2C, which is on my peripheral board connector, is actually the I2C4 of the STM32. That is a detail of that connector when it is put on the core board, and it is a different one if I go to a Nucleo board. But it doesn't matter for the sake of the peripheral board. And that's what's now been resolved at that point. So in my actual if I look into my peripheral board now, things have changed dramatically. I'm now making only references by this labeling scheme to these peripheral interface symbols, which could go wherever, and the machinery is just working for me in the background. And I have then the analog front-end SPI, and I can do this. So whenever I have a board that offers me these symbols, wherever they come from, my peripheral board will work again. And I do not need to change the software again, as I wanted to. And that's what it eventually looked up for the Nucleos. It's a bit, we had to introduce one more abstraction. We had different Nucleos, like there is this Morpho connector on the Nucleo boards. We had to make one more board, indeed, with the guys in Berlin, where the peripheral board connector, which was a single 60-pin connector, had to be mapped to the Morpho connector. So we were basically plugging the Nucleo board on some board where there was just a connector, and luckily we could buy the connector still back then. And then the connector was going to the peripheral board, pretty much like what the core board was doing before. And the invocation changed slightly again. We now are saying, give me the firmware for the F767, and then we had to apply a couple of mappings. It's a Nucleo 144. We had to do the Nucleo Nexus, which actually is a physical board, and the peripherals board. And we still could do version 1 and version 2. That was working as before. I think I switched to, and this is what I said earlier. These symbols need to be defined somewhere. Here you see it defined on this Nucleus overlay, where it actually goes to these connector labels, so label to label, where in the original core board or control board, it was directly going to the microcontroller. But the peripheral board, as a client of all of that, sees nothing from this. So that is the beauty of the device tree at this point. And then reality knocked again and said, yep, I can get you 80 of those 767, but not 200. So what we then had to do is actually, we had also to pick up 743s and 745s. But the main work had already been done at this point. All the abstraction were now working for us. So it was absolutely no problem for us then to do any of these combinations just with these invocations at the command line. The point is we did never ever change a single line of code for this. It was all at the abstraction level of the device tree. And it would build the very same firmware for all of these hardware variants. And that was the flexibility that we needed, because we had like 20 of those, 80 of those, 60 of those, and whatever number we had of those. So we eventually made it to the 200. And this is pretty much the end of my talk, but the moment of true love is still missing. So what's the moment of true love? Point was, we also had an application control board of our own, because eventually it's a typical design in medical devices. You do the HMI on an IMX8, IMX6, Linux stuff, and you have real-time control. And all I was talking about so far was the real-time control. And typically, on our application control, we had a private Ethernet running between the real-time control and our IMX8, and then we had a publicly facing Ethernet for just talking through to the rig with some web browser. We couldn't build these boards. We couldn't build these boards, so we had to resort to Raspberry Pi 4. Now, the good news is we could buy Raspberry Pi 4s, and I think we became the single most wanted dealer of Raspberry Pi 4s in the UK when we did that, because I think we bought like 1,000. Or actually, my client bought like 1,000. But the problem was it only had one Ethernet, and we needed that Ethernet. So we were missing this Ethernet. And yes, we could have used Ethernet USB dongles that would have worked, but they were clumsy and they were not very stable, and it had to be put into rigs. And there was, as we learned, a much more elegant version, because all the abstractions were already baked into what we were using. So what we were saying is actually, tell you what, let's not use a Mac, let's not use a PHY of Ethernet, just let's run virtual Ethernet over USB. And it just worked. We just made these 2 lines or 3 lines of change, recompiled the firmware, never even touched a header, nothing, just these 3 lines in a Kconfig, and it worked immediately. And this is when I fell in love with Zephyr. Thank you very much. Questions? Yes, yes.
It's not like off the shelf. Like
No, no, no.
how quick is your supply like in general?
It depended on, if it's only one function, you can actually be really quick because it's a connector and maybe one or two ICs. If you start to merge things together, then the longer it will take. But we managed to do these peripheral modules like in 2 weeks. If time is really at a premium and you're willing to pay like whatever 3 days expedite service for PCB, you can be really quick. You can do an iteration in 2 weeks. Typically, we found that's too fast, doesn't matter. 4 weeks is still good enough and way faster than most hardware shops actually work. So even 8 weeks is still faster than most hardware shops work. Yes?
In your case, this reduces a lot of complexity as you explained. You're playing with all these interfaces.
Yeah.
What would you say from what kind of complexity of product overall or team size will such a design work out? Like I can imagine for very small projects, there might even be some overhead.
There is some overhead initially, for sure. I'd say it pays off for, like in my instance, for medical devices, where first of all, the development phase is already like a couple of years, 2 years, 3 years, 5 years. So you really want to make sure you can go back to whatever you did in year 1. So you really want to have that history. Then it pays off. Obviously, it's with every abstraction as a trade-off. You have to put in work up front that might not pay off, like you ain't gonna need it. So it's still a bit of experience, I'd say. But this project, we were at peak 120 hardware, electronics, software engineers working on this, including the application control, I have to say. So maybe the real-time stuff was like 30 people. Yes, 120, yes. Yeah, and that was combined Yocto, and that's why I said, that's why you need a system architecture. To keep these things on track, you have to have this model, and you need to know what the people are doing, and they need to have a picture that they can come back to, yeah. Yeah, cool.
Can you elaborate more? How did you first? You said you talked about the open closed architecture.
Mm-hmm.
How did you choose which module to be on the left side, and how choose the connection to the right side?
That was no, it was where was it? I think here it was, right? Yes, this one. Yes. This list, actually, I reduced this for the sake of the presentation. There were actually more services in what we used up or what we ended up using. The idea is whatever, like in serverland, you might call it a microservice, so a distinguishable functionality. And for me, the point was, can I switch it off without affecting the rest? Would it still make sense to have a data scope and a shell, even if I cannot do remote procedure calls? Or can I switch off the shell and it would still work over MQTT, RPC, and a data scope? So these things are like orthogonal. I can switch them on and off at will. And then the functions are also orthogonal. That helps a lot when you do debugging. If you bring up a new module like the heater, you just might just decide to not bring in motor, and you do not bring in the AFE. Maybe because the soft firmware guy has only been given the heater module and the core board. So he doesn't even need to have the motor board and that. And you can switch that off as well. So that's also orthogonal. And for these things, Kconfig is ideal. That's exactly what you can do with Kconfig. Yeah.
Sorry to interrupt. We can continue the questions. So we'll start with 15 minutes break time. So feel free